So Moore's Law continues to be very important and relevant to our industry. It's important to recognize that Moore's Law is a law of economics. As you scale transistors, they get smaller, but they also are cheaper to produce. And you really need that cost reduction to justify chips and products that incorporate more transistors to provide more functionality. So today we have 10 nanometer technologies. In a few years we'll have 7. And in our research group, we see options to continue scaling to 5 and eventually to 3 nanometers. So I don't yet see an end to Moore's Law, even though we've gotten down to single digits for the node names. It was several decades ago now when ITRS was first formed. This is a committee of industry representatives who would try to outline the roadmap for the industry. But I think that roadmap began to lose a lot of meaning when the industry had to start doing revolutionary changes, such as introducing high-K metal gate, introducing FinFET technologies. So I think the importance or the relevance of an ITRS roadmap really lost a lot of its meaning several years ago. And now maybe a group of people have formed a new ITRS that claims it's no longer depending on Moore's Law, and I think they are misguided. The semiconductor industry, which has been going for more than 50 years now, has always been a very competitive industry. The players, or the leading players, may change from year to year or decade to decade, but today the industry is still very competitive and, in my view, will continue to be competitive for many years to come. So our industry, over its 50-plus years, has always depended on improvements in lithography and, in some cases, reduction in the wavelength of light to provide improvements in patterning and improvements in transistor density. For about 15 years now, the industry has gone through an unusually long period of staying with the same tool, the same 193 nanometer wavelength tool. So that's unprecedented. But we've been able to continue to provide better density, smaller features by introducing patterning innovations such as double patterning and now quad patterning techniques. But I think we have taken that as far as a 193 nanometer tool can go, so it's really important going forward that we have extreme ultraviolet wavelength tools with a 13.5 nanometer wavelength to continue future scaling. So let me point out that EUV with a 13.5 nanometer wavelength is a significant improvement over the previous or the existing 193 nanometer tools. And initially that will enable important process simplification. We can use EUV tools and use simple direct patterning. But on the generations that follow the first EUV generation, then we can start reintroducing some of the innovations that we tried on 193. We can try EUV with double patterning, and then EUV with quad patterning, and then maybe improved EUV tools going forward. So I think EUV is an important step in enabling several generations of scaling. Well, we are continuing to explore other patterning technologies besides EUV, but I can't talk about them now. It is true that on recent technologies we have to add more process steps, more masking steps to enable scaling, and that increases the cost of manufacturing those wafers. So that is a challenge. But Intel has found ways to scale the dimensions of our transistors at a faster pace than in the past, and as a result that smaller transistor area combined with the higher wafer costs still for Intel delivers lower cost per transistor. So for many years Intel and others in our industry have used node names to describe each new process technology, 45 nanometer generation, 32 nanometer generation. And those node names were usually reasonably accurate in describing the density advantage of the new generation compared to the past generation. And different companies in our industry, if they used the same node name, they were generally about the same transistor density. But that has changed on recent technologies where some other companies are using node names that sound aggressive, and yet they really aren't anywhere near the transistor density that Intel is providing on our 14 and now our 10 nanometer technology. So I felt it was important, or that there was a need to introduce what is actually an older metric that looks at the transistor density in important logic cells like a 2-input NAND cell and a scan flip-flop cell, and report that as the density of a technology. So when Intel described that metric, we can now describe our 10 nanometer technology not just by that node name, but by the fact that it delivers logic transistors with a density of around 100 million transistors per square millimeter. And that density is about twice as good as what other companies have on what they call their 10 nanometer technology. So node names today have become pretty misleading for both some members of the press and the public, so I think it's important to go back to a more quantitative density metric. So in both cases, what's similar between our hyperscaling N14 and our hyperscaling N10 is aggressive scaling of the important feature sizes or dimensions, like scaling the fin pitch, transistor gate pitch, the minimum metal interconnect pitch, and the height of the logic cell. So that's somewhat common between the two. They both are aggressively scaling those dimensions relatively to their previous generation. But what's new and unique on our 10 nanometer technology is two other innovations. Number one, a special process flow that allows us to reduce or eliminate the number of dummy transistor gates at the edge of each cell. So instead of having two dummy gates, we have only one, so that makes the logic cells more densely packed. And the other important innovation, which is a first in our industry, is to allow transistor gate contacts to be placed directly above the active gate as opposed to off to the side. So all previous technologies have put that gate contact off to the side. Now that we have a special process flow that allows it to be right on top of the active gate, our logic circuits can be laid out more densely. So it's true that recent technology generations like Intel's 14 and now our 10 nanometer are more complex technologies and have taken longer to develop. So instead of being spaced about 2 years apart, it's more like 2.5 or 3 years apart. With that being the case, it's still important to Intel's business to be able to introduce new products on an annual cadence. Products that either use the new technology going from 14 to 10, or new chip architecture or new chip design, or now also enhanced versions of our technology. So we are also following a plan to do a 14 nanometer technology, then a 14 plus, then a 14 plus plus, and now 10 nanometers followed by 10 plus and 10 plus plus. And those enhanced versions have most of the same design rules as the original version, but provide improved transistor performance and performance per watt. Improving transistor density has 2 or 3 key benefits. Number one, improved density means you can pack more transistors onto a chip and perform more functions. It can be more cores for improved performance, or more graphics execution units for better graphics performance. Also, scaled transistors have better performance and power characteristics, and it's true that for most applications, increasing performance is not always the number one goal. Today, users, the buyers of our products tend to value power reduction. So when we develop a technology with scaled transistors, we provide improved performance per watt, which means you can provide either a performance improvement or power reduction or some combination of the two. And again, lately, it's power reduction that's more important. Whether you're buying a mobile chip, and you want longer battery lifetime in your cell phone or your laptop, or the large data center, those buildings take a lot of power to operate and to cool, and our customers in data center really value the power reduction of our technologies. Well, I think our process technology does provide advantages or improvements in performance per watt, whether it's done on an x86 architecture or an ARM architecture. So I think it's really a benefit for both types of architectures. So you're wrong if you think Intel announced that we will abandon silicon at 7. That's not correct. We have not made that announcement. But I think we have, in various forms, announced that we are exploring a range of transistor types for the future, including transistors that use 3-5 materials instead of silicon for the channel. I can't tell you exactly when that will happen, when that will be adopted, but we have not announced the end of the use for silicon. Well, there are always some very novel and revolutionary technologies that people explore, or we are exploring at Intel, that might replace silicon, but silicon is just too darn good to replace right now.